Welcome back everyone. Last time we simulated some well-known physics problems with the help of Python. This here, for example, is the movement of a three-body system. With the solver we wrote, we can simulate any system as long as we provide it with the underlying differential equation. As I promised in that video, I am hard at work on the next episode, currently working on heat dissipations. But with my new semester at university having started, that video still needs some time before it's ready. So I thought in the meantime I'd show you another project that I have been working on. And that is moving our simulations to real time. As of right now, our solver is a bit like a black box. Not in the sense that we don't know what's going on in there, we wrote the code ourselves, but in the sense that we can't interact with it. The solver takes in the differential equation in the form of a function, and some other parameters like initial conditions, end time, and so on. And then, after some computation time, it returns a list of times and positions. Say these y values are the angles of a pendulum. Then we can animate it by just looking up the angle at every point in time. If the time step is small enough, this gives us a smooth animation. This is also how the animations from last video were made. Now today, I want to be able to go in between two simulation steps and change something. For example, giving the mass a little push. And then, obviously our solver should be able to respond to it and continue to work with this new value. For this to work, we'll first need a user interface which can interact with the simulation. Initially, I started this project in Pygame because that's the library I'm most familiar with. But Pygame doesn't really support an easy way for anti-aliasing, so the shapes looked all pixelated. Instead, we're gonna be using Piglet today, or Pyglet, I'm still not sure on how you pronounce it. It's a similar library that also allows us to draw stuff onto a window. First, I wrote down the dimensions of my monitor and how big the window should be. I'll wrap everything in this interactive sim class, and with just a few lines of code, we can get an empty window on our screen. Just to make it a bit more interesting, I'll simulate the elastic pendulum from last video instead of a regular one. So I'll rewrite the visualization in Piglet. It's just a bunch of primitive shapes, and by now I'm pretty good at doing the logic for these spring corners. Alright, with the variables here, I can now set its position. R0 controls the length of the spring, and T0 the angle. So pi over 4, for example, gives us 45 degrees. This is another reason why I like Piglet more than Pygame. It natively works in radians. Pygame uses degrees, which makes for some tedious conversions. Now, setting the position by hand is a bit laborious, so we will schedule this update function to be called, say, 60 times a second to animate smoothly. For example, I can increment the angle by 0.1 each frame. As we expect, this makes our pendulum just spin around. Instead of just incrementing the angle by a fixed value, we can apply our simulation to the system and calculate the next theta value with our solver. Before, we always chose quite a big value for T1, so something like 100 seconds to get a long animation. But now we want to know the position of the pendulum at the next frame, so after 60th of a second. And just like that, we're simulating the spring pendulum in real time. It shouldn't look too different to the animation from last video, but I guess with the chaotic nature of it, you never know. I also tweaked the solver slightly to only return a single value, since we're not interested in the ones between anymore. The last step towards interactivity is user input. Luckily, we can also handle mouse and keyboard presses with the Piglet library. I'll make it so that pressing the left mouse button gives the pendulum a little push. So if this function is called, we increment the angular velocity by, say, 1.5. I'll also introduce some damping, so that the pendulum doesn't just infinitely gain energy through our pushes. And just like that, we can interact with our pendulum. If we push it at the right time, we can give it quite the momentum, even with the damping. I know the interaction is really basic for now, but it's already quite fun to play around with. Next, I wanted to make it so we push the pendulum away from the mouse. I wrote this class here to display an arrow in that direction when I hold down the mouse button. It also changes length and color depending on the distance, which symbolizes the strength. And on release, we just change the velocities of the pendulum. Now, the push should be applied to both the R and theta component, so it took some trigonometry to determine the right ratios for that. Okay, so let's give it a proper test. If I run the code here, we get the window with our pendulum, and with the mouse I can charge the push here. Now, when I was initially developing this, I had it the other way around with the push. So the push would be greater when I'm closer to the pendulum and weaker when I'm further away, but somehow it feels more intuitive this way, like almost like you charge the push. Also, what I found myself doing a lot while testing it is to just speed up the pendulum a lot, so give it a lot of momentum, and then try to slow it down, so we can try to give it a push in the opposite direction always. And I know there is some inherent dampening, but it's not that strong, so it does spin around for quite a while if you don't try to stop it. I don't know why, but this always was a lot of fun to do, and see, there you go, now we stopped it a bit. And can we bring it to total hold? Yeah, okay, I think this is pretty good. Now, I don't know why, but even though it's such a simple simulation, I spent more time than I'm willing to admit just playing around with it like this. So yeah, I'm really happy with this. Next, I want to modify the double pendulum. I'll skip over the basic setup because it's pretty much the same as before. The only thing that really changes is the visualization of the pendulum and the differential equation, both of which we covered in the previous video though. So here we are with our moving double pendulum. My idea was to make it electrically charged. So the end here, for example, would have a positive charge, and then I could assign another charge to my mouse and push or pull the pendulum with it. Well, turns out even deriving the differential equation for a charged double pendulum isn't that easy. After about 2 hours or so, I managed to finally get this result. As a Python function, it looks something like this. It's still not pretty, but I think we can work with that. How we're gonna use it is that we'll fill in the first 3 parameters each frame. So set the XY position and the current charge, while leaving the rest of the structure intact. In Python, you can do this quite easily by wrapping the function with this lambda keyword, and then just supplying the position and charge each frame. If I run the simulation, we can already see it working. However, I think it's a bit difficult to tell what's going on, so I want to visualize the charge of the mouse somehow. For that, I started looking into shaders. Drawing a lot of individual pixels on screen can quickly become an issue. The CPU just has a tough time doing that because it executes our Python code line by line, and that takes time. I actually ran into this issue when I was coding the heat dissipation that you saw in the intro. They're generating this about 900 by 600 image took well over 10 seconds, so no chance we ever make it interactable. So instead, we can call on our graphics card. And by using a language it understands, for example GLSL shaders, it can draw much quicker by running this code in parallel. This here is a very simple implementation to draw a circle that fades out around the edges. But as you'll see in the next video, we can do much more powerful things with shaders. Okay, so let's see the final result. So again, I have everything set up here, and if I run the code, we again get the same window as before, and right here we have the double pendulum. Now, you can already faintly see this gray circle around my mouse. That's supposed to show kind of the effect of the charge. So right now it's gray, right now it's neutral, I'm not pressing anything. So we're not exerting a charge on the pendulum. I made it so that it starts in this rest position so you can kind of get used to this charge here. Now with the mouse wheel you can scroll up and down and make its effect bigger or smaller. That then also corresponds with the strength of the charge. And now if I press the left mouse button, you can see it changes color to red. And well, since the end of the pendulum is red, that symbolizes a positive charge. And then if I hold down the left mouse button, I also have a positive charge on my mouse, and it repels the mass at the end here, as you can see. And with the right mouse button, I can exert a negative charge, which then attracts the pendulum. Yeah, now, you see, you have to be a bit careful with the simulation. You can't, or you shouldn't really get too close to the mass here, because what happens there is it just spirals out of control. And that is obviously because the strength is inversely proportional to the distance, or I guess distance squared for the Coulomb force. So let's try to slow it down again a bit. So if you get too close to the pendulum, it just gets an unreasonable amount of acceleration. And yeah, it just because of the nature of the pendulum, it just spirals out of control and just has this chaotic motion. So again, let's try to slow it down a bit. I'm just trying to repel it at the right time to slow it down, but I think I just gave it more energy again. So, okay, I think right here is pretty good. So yeah, it works really well. Now, I also included the option, I think as you can see here in this documentation a bit, that you can also charge the middle joint right here. I left it uncharged because it doesn't have a color, so it's not that clear that it's charged, and the motion wasn't really intuitive that we had when the pendulum, or like when the middle joint right here had a different charge. But yeah, all in all, again, it's really fun to play around with. You can like try to balance the pendulum right here, for example, by repelling it, or let's stop it a bit, or you can also try to lift it up, maybe increase the effect of the pendulum of the mass. You can try to kind of lift it and then hold it like this and repel it maybe. So yeah, it's really also fascinating to me, even though these simulations like this one and the one before are so simple, it's so mesmerizing, and it's just really fun to just play around with them and to actually see this physical system interact to your input. To close off this video, I want to revisit the 3-body problem. Again, with the help of a shader, we can get a similar glowing effect in Piglet to the one in Blender. I'll be honest, I didn't bother making a shader for the trail. I'm not really sure how to do that, and I don't want to spend too much time on this tangent here, and rather focus on the next video. If you have any suggestions for that, do leave them in the comments below. I'd be genuinely interested to see how the trail is done with a shader. For this simulation, I want us to be able to control one of the planets with the mouse. The implementation for that is almost the simplest of the ones we did today. Each frame, I set the position of the third planet to be the mouse coordinates, and from that we calculate the movement of the other two. Now, because there are no actual walls or anything, the planets can just fly off into infinity. At least it happened to me often enough during testing that I came up with a fix. I didn't want to limit the movement with walls or something like that, so I wrote this function here to call them back with the spacebar. So let's switch into the view of the code editor one last time today. And in here I can now run the file, and when I do, the simulation starts instantly, and you can see the bodies interacting with each other. So we are controlling the light blue one, and then the yellow and the green one are interacting with each other as well as with our body. Now, what I'll have to say is that this is definitely the simulation that is the hardest to control and to try to produce a good result. Because, for example, we almost lost the yellow one, but you can see how easy it is for the planets to just fly off into infinity. Now, once you get a feel for it, you can actually make some really interesting interactions with that. Now, I want to show, for example, like this, we just lost the yellow one and there goes the green one as well. We can call them back with the spacebar, and as long as they are not too far away from the screen, it looks fairly okay and works really well. But for example, if I give the green one now a lot of velocity, and we now let it fly a while, and then call him back, you can see that now he has even more velocity. It's just because of the way how I coded it that the planet gains velocity depending on its distance, and then gets slowed down when it's closer. Now after a while, you can see it actually slows down and then returns to the position. So you shouldn't let them stray off too far for this to work. But I still prefer this one because it produces the most almost natural looking results, where we just give them some velocity. Now, you can't really tell at first glance, I guess, but the green and the yellow planet are actually heavier than our blue planet, which means that they interact more with each other than they interact with us, or with our planet. Just during testing I found that this produces a better result, because before that they would mostly just fall towards our planet and not really interact too much with each other, so we wouldn't get these nice shapes. So I found that these values work better. Now, I still have to say that I think my favorite simulation of today is the first one, the spring pendulum. I don't know, there's just something so satisfying about just being able to push it and then it responds to that. But the 3-body problem is also very beautiful, especially with this shader here, even without the trail. Unfortunately, these were about all the interactive simulations I could think of without repeating too much of the same concepts. As you already saw throughout this video, interactivity will also be a part of next episode. So this should serve as kind of an intermediate step to that. The idea behind, for example, the heat simulation is the same as interacting with our program today. Only the system is driven by a different equation, but more on that in the next video. In the meantime, you should try out these simulations yourself. I've updated the GitHub repo to also contain the files we talked about today. And if you've missed the first video, be sure to check it out here. With that, I want to thank you very much for watching, and see you in the next video.